And welcome back to one of the last videos in this little unit on um, atoms and electron configurations and some of the historical stuff about what we learned about the atom 100 and some years ago. The topic is periodic trends. As I look at the periodic table from top to bottom, left to right, what happens to fill in the blank? And the blank has about 4 or 5 different topics. Firstly, what about sizes of the atoms? So look at this little thing I clipped from the internet here. Hydrogen's a pretty small atom, of course, because it's, one proton and one electron. It's about 53 picometers, I believe. Yeah, zero point 0.5 angstroms or 0.05 nanometers anyways. Helium's a little bit smaller. What? Why is helium smaller? Lithium's 167 picometers. Beryllium's a little bit smaller. What? Why is that smaller? And smaller and smaller and smaller and smaller and smaller and what? I don't get it. Why do the atoms get smaller as I go left to right? Think about it for a minute. Maybe you know already. As I go down from top to bottom, oh, by the way, from left to right in the table, that's called a period, correct? So this is period 1, it's very short. Period 2 is also a pretty short period, and so is period 3, with n equals 3 and quantum number equal 3. Layer 4, a little bit bigger, quite a bit bigger, and it gets bigger as you go down. Oh, so the periods get longer as you go down, but more importantly, as I look down a column, a family, or group, it's obvious that the atom should get bigger because cesium has more layers of electrons, 6, than rubidium. And rubidium has more layers of electrons than potassium, 4. And potassium has more layers of electrons than sodium, 3. And lithium has more layers of electrons than hydrogen, 2. And hydrogen only has 1 layer. So of course they get bigger as you go this way. That kind of makes good common sense to me if you know something about how the electrons fill in around the positive nucleus. But as I go left to right, I'm not quite so sure I get that yet. Here's another cute little snippet, pretty blue and orange, about just the main group elements, ignoring the transition metals. There's no real need to ignore them here as I did with the valence electrons, but in terms of sizes, of course, they get larger as you go down, larger as you go down, larger as you go down. Helium 31, neon 71, argon 98 picometers. Yeah, krypton, xenon, radon, they get larger as you go down. But the confusing thing so far is why should they get smaller as you go left to right? Well, I'll tell you the answer right now. The answer is that even though, go back to this one, even though zinc has 30 protons and 30 electrons as compared to calcium's 20 protons and 20 electrons, the story is we think those 30 protons in the nucleus are pulling with more vigor upon those 30 electrons, pulling them into a smaller sphere. So even though as I go from left to right I do get more electrons, those electrons are placed in approximately the same distance from the nucleus, more or less, and the increased number of protons, positive in the nucleus, has a greater attraction for those electrons, those negative electrons, and therefore it ends up pulling that atom into a smaller sphere. So potassium is the smallest of the 4th period elements. Krypton, Kr, is the smallest of the 4th period elements. Then I go back up here, I bump back up again to a larger size, smaller, smaller, smaller. There's some burps, smaller, 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 smaller. Burp, a little bit of a burp, smaller, smaller. They generally get smaller. And again, left to right, gets smaller. The atoms get smaller because they're pulled into a smaller sphere by the increased number of positive charges on the increased number of protons, positively charged in the nucleus. If you like a graph, here it is. Hydrogen, helium, gets a little bit smaller. Then I bump up to n equals 2, period 2, and then it goes smaller and smaller and smaller till neon. Then I bump up to sodium, and it goes smaller and smaller and smaller to argon. Then I get bumped up to potassium, and smaller and burp, and smaller and burp, 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 smaller, smaller, smaller. The transition metals often have little burps or irregularities in their electron filling and also some of these trends. But for the most part, across the period, it gets bigger to smaller. Here's another more complete graph if you enjoy that kind of thing. It's a nice one. Can't complain. Can't see anything wrong with it. But it does illustrate the larger your atom gets, the more burpiness it has in this trend. But memorize this trend. More importantly than even memorize the trend is memorize why the trend happens. Again, top to bottom, the atom gets bigger. Left to right, the atom gets smaller because it's pulled into a smaller sphere by the increased number of protons in the nucleus. So if that's true, what happens to the ions of those atoms in terms of sizes? Well, first of all, there's an important difference between a positive ion and a negative ion. A positive ion has lost electrons, so it actually gets smaller. Those electrons are negatively electrically charged, so when they get removed from an atom, the atom gets smaller. So lithium, this looks like angstroms probably now. 1.3 angstroms, lithium atom. Lithium ion gets smaller because the lithium ion lost electrons. Lithium loves to lose an electron, sodium likes to lose an electron, potassium likes to lose an electron. First family elements, the alkali metals, they have a one valence electron. They love to lose that one valence electron in chemical reactions. So it makes them so reactive. And as they lose one electron, they all become positively charged. And of course, the ion is smaller, the ion is smaller, the ion is smaller than the atom it came from. Same story for the 2 plus family, the group 2A, beryllium, 0.9 angstroms, but I lose 2 electrons and I get smaller. 1.3 angstroms for magnesium, lose 2 electrons. Calcium loses 2 electrons. Strontium loses 2 electrons. Boron likes to lose 3 electrons. Same for aluminum, and it gets smaller. So positive ions, the cations, are smaller than the parent atoms from which they came. On the other hand, what about the nonmetals and the negative ions? Well, if you gain a negative electron, you get larger. I guess that makes sense. So if a fluorine atom has 0.7, probably is this diameter or radius? Dang, I don't know. This could be diameter, whatever. The relative size of fluorine, 0.71 angstroms. But if I gain to become a fluoride ion, which the group 7A elements sure like to do, this has 7 valence electrons. This has 7 valence electrons. This has 8. 7, 8, 7, 8, 7, 8, 7, 8 valence electrons, and that makes it in electron configuration like a noble gas. So, they get larger, and the same for the oxygen family, because it likes to gain 2 negative electrons. Gaining 2 negatives, gaining 2 negatives, gaining 2 negatives makes you more negatively charged, but also larger because those electrons have to go around the nucleus, and so it just makes the atom larger. So the trend is still the same. As I go from left to right with a particular positive group of ions, they get smaller because this one and this one and this one gets pulled into a smaller sphere by the increased number of protons in the nucleus. So the ions also get smaller as you go left to right, as long as you maintain the positive ion, and of course they get larger as you go top to bottom. This is small, big, small, bigger, bigger, bigger. Same story here, super small, bigger, bigger, bigger. But in the same trend here, small, bigger, 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 small, bigger, bigger, bigger. But if I go left to right, from here to here, they get a little bit smaller, a little bit smaller, a little bit smaller, a little bit smaller. Think about it. Here's another really cute one I thought I'd share with you. Shoot, you can Google this. You'll find this on the internet if you want to. Same story. Positive ions smaller, negative ions larger, and the trends still continue. Now, let's look at another trend like reactivity. Overall reactivity, especially reactivity, say, with water for the alkali metals. I'm sure you'll see this as a demonstration, perhaps, or on video. Lithium is reactive with water, sodium is reactive with water, potassium is reactive with water. These are all reactive with water. But as I go down the family, I increase in my reactivity. So cesium in water is pretty darn scary. Potassium in water is just fun. Well, of course, it depends on how much you're talking about. But I'm just saying, this cesium as an element is even more reactive than the potassium. Yeah, wonder why that is. I'll let you think about it for a second. come back to it. Or magnesium is less reactive than sodium. As I go from left part of the table to the right or toward the center, these elements typically get less reactive. I'll let you think about why that is as well. Over on the other side, ignoring the noble gases because they don't react with anyone, on the other side, as I go up, I get more reactive. So fluorine, can't even see that. Fluorine, chlorine, bromine, pretty reactive. So same for oxygen. But as I go over to carbon or phosphorus, as I go to the left, they get a little bit less reactive. You can memorize that and think about why it is. But sorry about that. Hang on a second. I try to get rid of that. Fiddlesticks. Where am I at? I'm here. Go back to here. Get rid of that. I apologize for that. Think about why it is. Oh shoot, I'm going to tell you right now. We already knew this trend. As I go left to right, they get smaller. As I go top to bottom, they get larger. So it seems like as I go down and left, francium and cesium, very, very, very reactive. Barium's pretty reactive. These are very reactive, and they're very large atoms. The reason why they're so reactive, being large atoms, is they hold their electrons very loosely. Those outer electrons, cesium is element 55. 55 protons, 55 electrons, but only one of those electrons is in the very outside, and therefore the reactive electron, the electron available for reactions. But that one electron is so far from the 55 positive protons in the nucleus, it's not held very tightly. So the more loosely an atom holds its electrons, probably because it's a large atom, the more reactive it is. Conversely, skedaddling up to the top right, and again ignoring the noble gases, they don't count because they don't react. You might remember why. Fluorine's a very, very small element. Being very, very small, it holds its electrons very, very tightly, and as a matter of fact, it would like to gain one more electron. But it's so small and so tight, those electrons are so close to the nucleus that it can pull electrons very strongly. That's actually called electronegativity, and we'll get to that in chapter 4. Maybe even chapter 3, pretty soon. So the very, very small elements, very reactive. The very, very big elements, very reactive. The big ones are reactive because they want to give up their electrons. The small ones are reactive like oxygen, fluorine, chlorine because they want to gain. They're very small, they want to gain electrons. Ionization energy, second trend. Energy required to remove an electron. Let's see what happens. As I go down a family, looks like the ionization energy gets less. Does that jive with what we just said about how well an atom holds its electrons? It does. So as I go down a family, the atom gets larger. The atom gets larger and the outside electrons are further from the nucleus. Being further from the nucleus, they're easier to remove. So cesium, easy peasy to take away an electron. Hydrogen, lithium, a little harder. But especially compared to the noble gases, they're very hard to remove an electron. This is like the kilojoules. If I had a mole of helium, 1 mole of helium looks like it would take about almost 2,500 kilojoules to take away 1 electron from a mole of helium atoms. That's actually a lot of energy. Fluorine also requires a lot of energy to take away electrons from. The ionization energy, the energy needed to take away an electron. So as you go down a family, down a family, down a family, indeed the ionization energy decreases because the atoms get larger. Larger atoms have electrons further from the nucleus, further from the positive nucleus, easier to remove those. But what about going left to right? Looks like generally the ionization energy goes up, lower to higher, generally. Why would the ionization energy get larger as I go from left to right, generally? Let's see, as I go left to right, the atoms get smaller, bigger, smaller, bigger, smaller. And the smaller elements have their electrons closer to the nucleus. And being closer to the nucleus, they're more strongly attracted to the positive charge of the nucleus. Being more, that's a mistake, that should be bromine. Being more closer to the nucleus means they're held more tightly, and therefore it would take more energy to remove the electrons. Think about it. It's true. Or again, if you like a graph. Easy, hard. Easy, harder, 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 burp, harder, harder, easy. Harder, burp, harder, 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 harder. So as I go left to right in the table across the period, the electrons get more difficult to remove, the ionization energy increases because the electrons are closer to the nucleus. That's the trend once more in my own writing if you want to see it. And you go down, these elements down here are big and large and the electrons are far from the nucleus. Also, what if I remove more than one valence electron? Oops, yeah, it's a valence electron. So when I remove electrons, they're valence electrons, but I shouldn't say that as a blanket statement because consider sodium. The ionization energy for the first electron being removed from sodium is pretty small. That's called I1, ionization energy 1. But what if I wanted to take another electron from sodium? Whoa, why is it so much harder, almost 4,600 kilojoules, to take away the second electron from sodium as opposed to just the first? Or consider magnesium. Take away one electron, take away two electrons, take away three electrons. I wonder why they drew this blue stair-steppy thing here. Consider aluminum. Take away one electron, take away two electrons, take away three electrons. But on the relative scale of things, taking away the fourth electron from aluminum is very, very difficult. You know why that is already? Because sodium likes to lose one to look like, let me come up here to the table. Sodium wants to lose one electron so that it can look in configuration like neon. Magnesium wants to lose one. If it loses one, it looks like a sodium in electron configuration, but magnesium likes to lose two electrons to have 10 electrons, still 12 protons in the nucleus, but 10 electrons makes it have electron configuration like neon. But if I tried to take away one more electron from magnesium, so the third electron is like taking an electron from the noble gas, which is very, very hard, even more difficult because there are more protons in the nucleus, even still. So taking electrons from a noble gas or an electron configuration of a noble gas, very, very hard. Think about it. That's a good one to think about. And the last one I have is called electron affinity. Electron affinity is the energy change that goes along with the addition of an electron to a gaseous atom. As it turns out, many, many times when you add an electron to an element, even if it's a metal that doesn't necessarily want the electron and may not end up keeping that electron very long, almost always energy is released. And when energy is released, we say it's exothermic. And so, according to our convention, what we're agreeing to agree upon, these electron affinities are always negative. Not always, oftentimes negative. Not always true. Here's the trend. Slightly interesting and confusing. Let's see. These are all positive electron affinities because I would have to add energy into these noble gases to force them to take on an electron. Curiously as well, you might try to explain this if you feel brave. Why is beryllium and magnesium also a positive electron affinity? Why would I have to add energy into these to a beryllium to force it to take an electron? Whereas almost all the rest of them are negative. I wonder what the trend is. So if I add an electron to lithium, they give off energy, but it looks like it gives off less and less energy as we go down the family. So it's I could say less stabilized down here than up here. The more negative the electron affinity energy, the more that ion is stabilized. But check this out over here. Fluorine's negative 330. That's the biggest number on the chart, I think. Oh no, what? Get out of here. 350? Alright, well, I'm confused by that for this minute. I can't rationalize that right away. I'd have to spend some time thinking about it. But generally, these nonmetals that like to gain electrons have a very negative electron affinity, meaning they give off a whole bunch of energy. When an oxygen gains one negative electron, it gives off a bunch of energy. And that's, in a sense, a way to say that it's more stabilized. So the oxygen becoming oxide is more stable, giving off some energy. That's a little confusing, isn't it? Here's another table I made up. Most electron affinities are negative. I say they're negative. It depends who you ask because it's exothermic. Some of them are positive. Honestly, we just saw above that these may not be too positive. They may actually be negative because they're larger, and the larger ones are easier to give a negative electron to. But yeah, that's a summary of the trend. As they go from left to right, the electron affinities get more negative. As they go from top to bottom, they get less negative. So as I go from here over to the top right here, electron affinities increase. I guess we could say the affinity is the desire or the propensity to gain an electron. Another table looking at electron, the nitrogen there is really confusing. It's tucked underneath between the carbon oxygen. And lastly, no, not quite lastly, I have one more summary slide. Electron affinities increase as they go from the bottom left to the top right. These elements are they're also called electronegative elements because they really want to gain electrons. I'll talk about that in a few videos. Here's a summary of most of those trends we've talked about. You can memorize the trends if you like, or even on a more fundamental level, it's perhaps even better to say why. Metallic character is sort of like the more further you are from the nonmetals, like down here, you're more metallic in character. Ionization energy, electron affinity, size of the atom, and I guess increasing is from the bottom of the arrow to the top of the arrow. So large atoms and small atoms. I'm going to stop there. Thanks guys, see you in class. Appreciate your time. Thanks for watching. Ask questions.